We have a lever arm here which is pivoting about at point O, and it has a cable attached to it. And this question comes from Schlenker, chapter 5, and it's number 21. Okay, so it's pivoting about point O, it's a lever, and it has a force of 100 newtons being applied at right angles to the lever, has a tension in a cable at B which is horizontal to the ground, and we're being asked to find out what is the tension in the cable and what is the reaction that's happening here. So it's going to be a reaction. I'm going to draw that in red over here. So there'll be a reaction, and we don't know quite what angle it's going to be, and I'm going to call the reaction RO. I'm going to call the tension in the cable TB, tension at B. All right. Now, we do know some things. We know the angle, the line of action of the force, and we know the magnitude of the force. We know its point of application and its sense, the 100 Newton force. We know everything about that force. We know the line of action of TB. It's going to be horizontal because that's a sliding pin over here, and no matter where we pull the lever, the force will always be horizontal. We don't know anything about the magnitude or the reaction at O, except that we know that it must travel through that point. So the force has to go through that pivot point. This is a classic three-force rule. There's only three forces acting here. Tension at B, the applied force 100 newtons through the top of the lever, and the reaction at O. So we know that all three of these forces must be concurrent. So the three-force rule says that all acting forces on an object, if there's only three of them, must be concurrent, which means all passing through the same point. Now the question is, where will that point be? Well, to find that out, let's see where this force intersects with the force that we know all about, the 100 Newton force, and it's going to intersect exactly at that point there. Now that's very useful for us because we know that the reaction at O has to travel through the pin because that's where it's being applied to the lever, but it also has to go through that point because that's the point of intersection of the other two forces. And if all three forces are going to be concurrent, all three will have to go through that point. So we can now determine the angle or the direction of the reaction at O. It's going to go through that point O, and it's going to go through the intersection of the other two forces on their lines of action. Now that's very useful because that gives us the angle of application of RO. And with the protractor, now I should be able to work that out. So let's line the protractor up. Now your accuracy of your answer is going to depend largely on how accurately you measure and you plot things. Now looking at that, it looks like it's pretty close to 5 degrees, maybe just a bit. I'm going to go with 5 because 5 is the actual right answer and it's going to give us a better result. But if you put 5.5, it won't matter. The thickness of your lines can make a huge difference. So we'll say that's 5 degrees. Now, having said all that, we're now going to plot a different diagram using just forces. Now, if you've done this diagram accurately, you can actually use your free body diagram, your space diagram, to plot your forces. If you haven't done it accurately, you can start again. I'll start again just to give you a bit of an idea so that you can find it easy to do. Now, in plotting this diagram, my first diagram in drawing it, I had a scale. It's very important that you draw your diagrams to scale if you're going to use graphical solutions. So my scale for that diagram was 1 millimeter on my diagram is 10 millimeters on the actual mechanical system. Therefore, my scale was 1 to 10. Now, I'm going to draw for my force diagram. I'm going to use a different scale because I happen to know that this is going to produce actually, I might use a very similar scale. I'm going to use, my scale will be 1 millimeter on my drawing is going to equal to 10 newtons of force. Very important when we come to calibrating our results. Okay, so let's travel a bit further down here now and start setting up our diagram. Now I'm going to use a thick pen, but you would normally use quite a thin pen to get more accuracy. Start with the base level. There's my baseline. And over here, I'm going to plot my point, and I'm going to make my reaction another point actually right over here. I'm going to change that. So I want now 45 degrees coming out. Now I can use a protractor if I wanted to produce my 45 degree angle. I could line it up there at 45 degrees, which will be here. Or I could grab my 45 degree set square like I have here, and I could say, all right, there's my baseline. I'll line up the bottom set square, which is a 30 on the baseline, and just move my 45 degree backwards and forwards until I can line it up with my dot. Like this. Either way will produce a result that we want. So there's the line of action of my 100 Newton force. It's going to go through here. Now, according to my scale, 1 millimeter is 10 newtons. So 100 newtons is 10 millimeters. So if I measure very carefully, and again, your accuracy will be important here. I'm using a thick pen, which is not ideal, but at least it helps you see what I'm doing. So I'm measuring up here. Make it a little bit larger for you. $10 millimeters to there. So that distance there is the equivalent of my 100 newtons force. Now, the next thing I know is, so I have that force acting downwards like this. There's my arrowhead. The other thing that I know is that I have another force which is going to be a horizontal force. Now, if all the vectors added head to tail end up forming a closed diagram, that means that the object's in equilibrium because all the forces are going to balance. And that's the case. This system over here is in equilibrium. You're pulling the lever, you're presuming it's not moving, all the forces are balanced, and you're just applying them and they're stationary. So if that's the case, then all of the vectors have to add head to tail, and I have to have a horizontal vector because that's my force at B. So I'm going to make the horizontal vector down the bottom here. Now that's its line of action, but I don't know how long it is. So how can I determine? Well, I have another force here which is acting at 6 degrees to the horizontal upwards, which means that angle there will also be 6 degrees. So if I create myself, and I'll drop out of here so you can see, a parallel reference line, so I can create a nice 6 degree line coming from the base of my, there it is. So there's the base. It's not a very straight line, is it? Yeah, and even by eye I can see that that's not very straight. Let me line it up a little bit better. That's better. I'll use this pen. Okay, so there's my reference point here. Now from here, I want to produce a line that drops down by 6 degrees to represent the vector that I've, or 5 degrees, didn't I? I said 5 degrees up here. 5 degrees. So I grab my line and I find my 5 degree point. There it is, right there. And now I'm going to create a line that's going to go through the base of my 100 Newton vector, and it's going to intersect this other vector, the horizontal vector, like that. Okay, so 100 newtons here, and my point of intersection is going to be just about, I'd say here. Now, I know that my horizontal vector, my tension's pulling in that direction. So the arrowhead of my horizontal vector will be coming in that direction to there. This force, on the other hand, the reaction force, is going to be pushing back, and it needs to push back in order for the force diagram to close. So this will be the direction of my resultant vector. So that will be RO from here to here, and this will be TB from the point of the 100 all the way to the end. So what are their values now? I know that this is 5 degrees, that angle. What are the magnitudes of the vectors? Well, I only need to measure them now. So if I measure and place my ruler on here, measure them nice and carefully, I'm coming up with this distance here being about 92 millimeters. So TB is going to equal to 92 millimeters multiplied by my scale. My scale is 1 millimeter is 10 newtons. So I'm going to write that as 10 newtons per millimeter. Cross out the millimeters. I'm left with 920 newtons as the force of TB acting horizontally to the right. What about RO? Well, RO, if I measure RO, it looks like it's 82 millimeters. There we are, about 82. So I can say RO is going to equal to 82 millimeters multiplied by my scale factor, which is 10 newtons per 1 millimeter. Cross out the millimeters, 820 newtons. And that's going to act at 6 degrees to the horizontal up to the right. So now I've solved graphically for the force, the tension in TB, which is this tension here, and you notice it makes sense. It's because we've got a mechanical advantage over here pulling with that long lever. We are got a high tension in TB, which is what we'd expect with a brake lever, and it's at 920 newtons for an input of 100 newtons, and I've got a reaction which is pushing up at a shallow angle of 820 newtons from point O. Very useful to know that. So there's the solutions. Now these vary slightly from the actual answers. It would be because the accuracy of my measuring with this thick pen will produce a substantial difference in terms of intersection points here, which then produces different measurements. So accuracy becomes everything when you're doing graphical solutions, but that's the correct method. Goodbye.